Hi, so I'm Andrew Yeung on the Microsoft graphics team. You can kind of tell from the shirt. My GSL shirt says Build Better Shaders. And today I'll be talking to you about direct storage for Windows. So why don't we just jump right into it? Here's a little bit of an agenda. It'll be a direct storage for Windows update. Last year we had actually posted a blog post about it, and today we're going to give you a little bit more detail about how it works. We're going to talk about the context of the journey to eliminate load time, something that nobody really likes. Spoiler, PC isn't there yet. Console's actually very far ahead. We'll talk about direct storage technology itself, how it's the next big step to eliminating those load times, and a couple of other scenarios. And then we'll talk about how to start building a direct storage ready engine. It's a paradigm shift. There's going to be some changes to your engine, and so we want to give you an idea of what that looks like. So let's start with the context. We want to give you a little bit of an idea of why this is a problem in the first place, what kind of experience users get, and how we want to go and make that better. But first, let's talk about how hardware fuels gaming innovation. And so in the hardware space, there's basically constant competition to continue building the best gaming hardware. And that will basically feed innovation into gaming experiences. In some cases, you might want to improve. 1 year, the industry might be trying to improve resolution. Another year, we might be trying to improve frame rate, go from 60 to 120 or from 30 to 60. And in this case, we also see hardware being innovated on to provide improved load times. And so we want to be able to take best advantage of that. And so let's take a look at a couple of examples. You have the components, you have the evolution, you have processor speeds. We went from kilohertz to megahertz to gigahertz. Display resolutions have also increased all the way up to 4K, maybe even up to 8K. In the next little while. VRAM has gone from kilobytes to megabytes to gigabytes, and the one that we really care about right now for direct storage is I/O speeds have made this leap as well from megabytes to gigabytes. And so we have to ask ourselves, well, I/O tech has improved a lot, just as any kind of piece of hardware improves. That doesn't necessarily mean that the experience itself will improve. And so what we see today is that I/O tech has improved quite a bit, and yet we still get these experiences where you only have a short time to play, especially in the pandemic right now, where you might want to just get in 15 minutes or 20 minutes of gameplay, and a lot of it's just loading times. That's not a very good experience. Another one, which I've encountered a lot, maybe I should get better at playing games, is every time I die, let's say you're 5 seconds, your checkpoint is 5 seconds before a boss, you get to the boss, you die within the next 5 seconds, so you've played only maybe about 10 seconds, and I have to wait another 20 seconds, 30 seconds to try again. Also not a very good experience, not something that I want to spend my day doing, just waiting. Another one, this is not really a load time related one, but we do see this today in modern games still, is when you fast travel, when you go from point A to point B, and you load this new area of the map, sometimes it looks like you're playing games in the 90s again, or the 2000s. If you remember, you have a character with a face that doesn't really exist. It's just a block. And then it starts popping in, and you have all the trees in the background. They start popping in. That's not a very consistent experience. It's a little bit jarring, especially if you're trying to, say, read a sign in the distance and you got to wait another 10 seconds before you can read what that is. And this is a little bit of a joke, but I'm sure people have felt this pain before. But you kind of walk into an elevator in a game, and you're trying to, and the elevator serves as a level loading mechanism, and it just feels like I'm playing an elevator simulator where I'm constantly pressing the button like a pedestrian light button, waiting for it to change or waiting for the doors to open so I can continue playing my game. It's basically an elevator simulator, and again, not a very good experience. And so we got to ask ourselves, are we really utilizing the hardware effectively? And these experiences, I shouldn't say experiences, if these bad experiences exist still today, even though I/O tech has improved, are we really using it effectively? The short answer is no. I/O hardware has evolved really, really far in the past little while, but it's beyond what software can accommodate. So there are a couple of bottlenecks, and we'll talk about those in a bit, but it essentially prevents it from getting the maximum potential out of that hardware. So let's take a look at an example. Let's say you're moving from a hard drive, HDD. A user is moved from an HDD to a NVMe SSD, an NVMe drive. There's a huge leap in I/O capabilities. We're talking 40 times faster on the Series X versus Xbox One. And that same magnitude of innovation exists on PC. And yet, we only see about a 1.5 to 3 times improvement on PC games if you just swap out the hardware and you play the same game, apples to apples comparison, you really only see 1.5 to 3 times. And so why is that? Why is it that I can have many tens of times more faster hardware and only get like 1.5 to 3 times improvement? Why is it that we're not taking advantage of the full bandwidth? How is that possible? And the short version is that there are several factors. CPU bandwidth is one of them. The paradigm that we're using to actually load the textures in or other assets is another one. And it boils down to essentially taking too much time to load too much data. And so how do we get down to that under 1 second load time North Star? That's where we really want to go, where it starts feeling instantaneous. Let's take a look at kind of high level how the data flows. You essentially have on the left side here, you have an NVMe SSD. On the right side, you have the destination. An example is a GPU. I use a GPU as the destination because a lot of the data that we want actually is destined for the GPU. And there are two factors that basically feed into the time it takes to load. And that's X here on the screen, X megabytes total. That's how much data you want. And then Y megabytes per second is kind of the rate at which you can transfer from point A to point B. And that basically means that the time to load the data is X over Y, amount of data over the rate of data being transferred. And so there's two things that you can do to minimize load time. You can either minimize X, which is the amount of data, and we basically consider that being smart about what you load, only loading what you need, and maximizing Y, which is increasing the throughput. So by doing that, minimizing X or maximizing Y, you can reduce your load time. And there are two features that we've built in the DirectX family for this. To be smarter, to help your engine be smarter, we've created sampler feedback. And to be faster, we've created DirectStorage. Both of these already exist on Xbox. Sampler feedback exists on PC, and we're bringing DirectStorage as well to PC to complete the picture. And so today we'll be talking specifically about DirectStorage. At the end, we'll talk a little bit about how sampler feedback and DirectStorage kind of combine together to give you a very modernized engine, which allows you to transfer all that data pretty quickly and only what you need. So now's probably a good time to remind you that we're always in the business of helping you maximize the potential on both Xbox and PC. The Xbox Velocity Architecture, if you've read about it, it lets you get the most out of your console's cutting edge hardware. It includes sampler feedback, it includes DirectStorage, and console being a single piece of hardware. Actually, there are two. All users will, a Series X and S consoles will benefit all at once. Now, on PC, the story is a little bit different. PCs aren't all the same, but we still want to enable you to get the most out of the available hardware, and that's what these features aim to do. A couple of examples: new GPU adds in feature, the gamers upgrade. That doesn't necessarily mean every single gamer has it all at once. It might take a couple of years. Some users just might be happy with what they have right now. Another example relevant to us in this particular talk is NVMe SSD prices drop. And what you see essentially is a sudden but not instantaneous shift of users to NVMe SSD equipped PCs. But again, not everybody has it all at once. And so what we strive to do with the DirectX platform, and what we're doing with all the features, is one converged DirectX platform plus the cutting edge features in that platform allows you to get the best games on both console and PC. We make those cutting edge features available where the hardware makes them available. And that is true on DirectX 12 Ultimate. It's true for DirectStorage, and it'll be true for future innovation. All right, and so let's get into the details of how DirectStorage actually works, how it's built, and how it's going to help solve the load time problem and texture streaming problem that we kind of called out before. We can start with an overall architecture. Here on the left, you can see kind of how it breaks down. The goals and design principles for DirectStorage are the same as Xbox. The APIs are very similar with only minor differences. It's kind of similar to how DirectX, D3D 12, I should say, is the same or very similar on Xbox and PC with minor differences. And then the implementation details will, of course, differ. The underlying technology of how you deliver the functionality for the API will differ on PC versus Xbox, although your developer experience in the application is going to be the same or very similar. And so for DirectStorage, there's kind of three primary components. You can see this on the diagram. There's DirectStorage Runtime and API. That's the component that your application actually talks to. It's the way that we abstract a little bit of functionality while giving you control over the hardware, pretty direct control over the hardware, but so that you don't have to build two implementations for two different platforms. You have the asset decompression piece, and we'll talk a lot more about this in a detailed slide later on. It's essentially powered by D3D. And we have the Windows Storage Stack. Windows Storage Stack being the component that allows you to pull data off of the disk for later processing, including asset decompression, and then transfer over to the destination, either CPU access or the GPU. And so it's important to realize that direct storage isn't any one of these components. It's actually a collection of these components, and the way that they work together to optimize the end-to-end data flow is kind of the mentality behind the direct storage effort. So let's talk a little bit about the scenarios, what scenarios we actually care about. And so we talked about the end user scenarios, but how does this look like from a technical perspective? What are the technical scenarios that back those experiences? And so the first one, probably the most relevant one, is copying data from the disk to the GPU for GPU usage. So the destination is GPU. That can be geometry, textures. Textures are a really big one, so we definitely want to call that one out. We also have to remember that we have situations where we want to copy data that's destined for CPU usage, like they don't go over the bus to the GPU or VRAM, essentially. And an example of that would be audio. The last one, this is very, very important for textures in particular, because there are a lot of textures make up a large part of your data set. And so we have to consider the situation where you have to decompress those textures to something that is GPU usage ready. And we're not talking about BC compression here. There's block compression, but then there's a secondary wrapper of compression around that typically that textures have. An example would be deflate-based compression on top of the BC format. So you essentially have a BC format wrapped, BC format texture wrapped by another decompression to make it disk space optimized. It's small so that the user doesn't have to install, say, a 500 gigabyte game. And then it's decompressed at runtime to become GPU usage ready. And at which point the GPU can use it to render the scene, et cetera. And so for future reference in this presentation, when we talk about decompression, we're talking about that outer layer of compression, not the inner BC compression. And so let's take a look at the flow of the GPU assets today. You know, what does it look like from point A to point B to point C? First, data, of course, starts on the NVMe SSD. The user had downloaded their game. The game package is on their drive. First thing we need to do is to get that data off of the disk. And so we have a storage read using the existing storage stack, Windows Storage Stack. You get it into system memory. That's RAM. And then at that point in time, a game will have to decompress this asset. And so they use CPU decompression. You decompress it, goes back into system memory. And then for GPU related textures, again, we're focusing on textures just simply because that's the most complex path that we have to consider. Then you have to copy to the GPU, at which point it can be used finally. So that's today. When we're thinking about the future with direct storage for Windows, we kind of want to move that decompression step to the end. There are various reasons for that, but overall, the picture now looks like you have the NVMe SSD with the game package. You do a storage read of the asset that you want, or the piece of the asset that you want. That would go through an optimized storage stack. Again, we'll talk about that a bit in a detailed slide. Goes to system memory. But at this point, you're not going to do the decompression. What's going to happen is that you can just do the copy directly to the GPU first. So you do copy to system, copy to GPU. And only then are you going to do the decompression. And so a couple of reasons why we want to do that. One, with the right decompression algorithm, the GPU actually supports far higher bandwidths for decompression, key for both scenarios of texture streaming and load time. The CPU savings are at next-gen I/O rates, so we're talking gigabytes a second, are really, really big. When we're talking about decompressing, say, 2, 3, 4 gigabytes a second, the CPU cost is extremely high, so you really want that higher decompression bandwidth on the GPU so that you're not bound on CPU. The third reason is the GPU can support a very consistent, constant maxed I/O rate. So let's say you have a drive that's capable of, say, 2.5 gigabytes a second. Your GPU is capable of maintaining that and focusing essentially on the decompression task for the entire 2.5 full maxed I/O rate for load time scenarios. completely offloading the CPU for any GPU destined assets. The data is actually at the smallest until its destination. What I mean by that is you take the compressed asset, let's say it's say 1 megabyte, just as an example, when it's compressed, and 2 megabytes when it's expanded, when it's fat. You only have to copy 1 megabyte over to system memory, and then you copy 1 megabyte, not 2 megabytes, to GPU, and then you decompress it, you expand it out to 2 megabytes. In the old world, you would have to copy over 1 megabyte first to system memory, you decompress it, then you're copying 2 megabytes over the PCIe bus or into a GPU accessible memory. And keeping it smallest to the very end actually makes you more efficient. You're using less bandwidth until you really need it. And then finally, doing this actually opens up the door to other optimizations that we can implement. I won't get into too much detail there, but there is an evolution to direct storage that we can look forward to. All right, so let's get into the details of each individual component. You have the DirectStorage API. It's essentially the newest addition to the DirectX family of APIs. There's D3D. DirectStorage is just another direct branded API. It integrates directly with D3D12. Essentially bridging the gap between storage and GPU technology. It introduces kind of a new calling pattern that optimizes for three specific things. One is to keep the NVMe SSD drive fed. That, as I was mentioning before, we want to make sure that we get the most out of the hardware. There are specifics around how an NVMe SSD should be fed to make sure that it delivers to you the bandwidth that you want, the maximum potential. It also manages to keep the GPU fed. For the same reason, the GPU likes certain patterns of workloads come into it to make it the most efficient possible, pipelining your work, batching your work. And finally, the DirectStorage API reduces application overhead. Now, fundamentally, high-performance scenarios these days are highly granular, meaning you deal with a lot of little small components, but very parallel, in which all of those can be done at once. And these essentially are workloads that like to have multiple requests up front, not necessarily doing one at a time, and only notifying you, the application, or notifying components when they really need to be notified. And that essentially becomes a batch workload. In the past, you might have seen games. You load the entire thing and then you go. Now we get down to the granularity of textures, and then now we get down to the granularity of MIPS. And we're going even further down to the granularity of tiles. That's highly granular, but you want to deal with a lot of things in parallel to be efficient. And so if you take a look at D3D12, this is the optimized model for leveraging GPU parallel behavior. A GPU, when you use a GPU, you don't draw one triangle at a time. It's not like you're saying, draw this triangle, then that one, that one, then that one. You actually send it a whole bunch of work to do, and it managed to do it in parallel very, very quickly for you. DirectStorage essentially introduces that same batched model, or it introduces a batched model, the same idea of leveraging the parallel behavior of the system and hardware. It applies that batched model to storage read requests, and it also bridges the storage stack with the GPU in a very, very efficient way. And that helps us maximize NVMe SSD performance, and also helps us remove any loss in efficiency between basically connecting those two subsystems together. An example, existing I/O APIs essentially treat every request individually. You have to make one request and you get a completion notification for one request. It's analogous to drawing one triangle and it telling you when you're done one triangle. In this case, it's you make one request for a piece of data off of the disk, and then you get a completion saying it's done. That's super, super inefficient, especially if you have a large number of requests, like hundreds, thousands, even tens of thousands of requests per second. You don't really want to be doing one at a time. So the DirectStorage API essentially allows you, the developer who's building the game, to create these batched requests and to identify when you want to be notified. If you have, say, 1,000 things that you need, you can say, I want these 1,000 things, and only when those 1,000 things are done do I want to be notified. It significantly reduces the application paperwork that you need to do to make sure that there's a lot less overhead overall. Let's move on to the next component, and that's asset decompression. A little bit of context here. Gaming has always been a trailblazer, pushing tech to the limits, pushing the hardware to the limits. And the biggest games, the most detailed games, they don't come for free. When you're talking 4K and in the future 8K, you actually need a lot of resources to supply that experience, a lot of data. And so these asset packages are really, really big, and they're compressed to fit on disk. They are decompressed at runtime. And so it's not like you're downloading, say, a 100 gigabyte package. You decompress it to 150 gigabytes or 200 gigabytes. The user doesn't really want a 150, 200 gigabyte package on their disk at all times. And so what we really see is the evolution of decompression technologies that decompress assets before you need them in the game while keeping them compressed on disk. And so there have been specialized CPU-based decompressors that were created for this exact purpose, for gaming purposes. But at the very high rates of today of NVMe drives and just the system overall, like PCIe Express, decompression overhead is getting really, really expensive to maximize the potential of that hardware. And so gaming has created the need for us to innovate in that space, but we really do need to make another leap. And so we need new innovation in specifically compression, decompression technologies. And so Xbox Series X and S, they have hardware accelerated decompression. That's part of the velocity architecture. That's one of the pieces to decompressing the assets that's available on Xbox, on the next gen Xbox. No such solution on PC. How do we really accommodate those high rates? Silicon being, in this case, chip technology, takes a long time to build. And again, like we mentioned, it won't be available to everybody instantaneously. And it's essentially unacceptable for us to say, as an industry, please wait a couple of years, we're going to go build hardware, wait for that to arrive, and then you can take advantage of the other hardware, the NVMe SSD drive. That is not really an acceptable scenario. And so instead, what Microsoft is doing is we're creating something called GPU-friendly decompression. Microsoft is working very closely with the GPU vendors that you know really well in a collaboration to innovate in that space and create a GPU-friendly compression decompression solution that essentially works on today's hardware. So you don't need to wait a couple of years for new hardware to arrive. It'll work on today's GPUs. This is a new class of compression technology. I won't get into the details, but it does have new requirements. Making a compression technology GPU-friendly, as it were, requires innovation in how the compression technology actually works. You don't really have to worry about that, but there are 3 components under development, essentially. There's a direct compute based decompressor that essentially allows us to run it on existing GPUs. There's an initial prototype that we have. It easily saturates gaming SSD bandwidth, and so we're pretty confident, we're pretty happy with the results and being able to enable you, the game developers, to take advantage of the full bandwidth once we're able to release direct storage. This also opens a door to further innovation. Just because hardware isn't available today doesn't mean we don't want to find a path to hardware. And so while we have a direct compute-based decompressor for bootstrapping and giving you something to start with to get those higher bandwidths, we do want to make sure that we enable hardware implementations in the future. There's a CPU decompressor for assets. Like we were saying, a lot of the assets are destined for the GPU, but not all of them. And so we do have to provide a CPU decompressor for assets destined for system memory. Audio was an example. And finally, of course, a decompressor is useless without a compressor. And so we're building that as well. Those are under development. This package will be part of the direct storage package that will deliver to you so you can take advantage of this technology. So let's take a look at the Windows storage stack. This is the last of those 3 components that I mentioned before. What we're basically doing here at Microsoft is optimizing Windows for high bandwidth and high IOPS direct storage scenarios. It's important to recognize that it's not just high bandwidth that you want, but because of that very highly granular and parallel workload, there's also a high number of IOPS. And so you can imagine your game, you have texture streaming, you have tiles. Those tiles are small, but you want to have a lot of them loaded in at once. we have to essentially make the system efficient for many, many, many small requests. We're not just optimizing for a single, many gigabyte size file. There are details around why. And so we're achieving this by optimizing path length and reducing CPU usage. The I/O stack bypasses certain parts of the Windows stack. Windows will bypass certain parts of the I/O stack in this situation. And we're reducing user mode and kernel mode transitions, and there's a big focus on reducing per read CPU overhead. This is a pure Windows OS improvement. You don't really have to worry about it, but we did want to give you a view kind of behind the scenes on what's going on. DirectStorage is automatically going to leverage the most optimized storage to access path depending on your PC configuration. So building a DirectStorage ready engine, this is something that we want to help you understand how to change your thinking. And this is essentially sampler feedback plus DirectStorage. There's an increase in game memory needs recently, and that's essentially increasing faster than VRAM is increasing on GPUs. You see games, they are going from 10 to 50 to 100 gigabytes in size. VRAM is not going from 10 to 50 to 100. The increase in VRAM is slower. And so we need to accommodate that. And that essentially demands that the game become smarter and faster. There are memory multiplier techniques that are very powerful. This boils down to being very selective with your data, and using sampler feedback can do that while having very, very fast asset turnover with DirectStorage, since you're going to be bringing data in and out. And it essentially makes your GPU look like it has X times more memory. If you only bring in, say, half as much data as you needed to before, let's say you have 5 megabytes instead of 10, because you're being very selective and you really said, oh, I only need those 5. What it really looks like is instead of, say, a 10 gigabyte GPU, you have a 20 gigabyte GPU because you're twice as efficient. And this doesn't just increase your load times. Decrease your load times, increase your load time efficiency. It also creates a path to bigger worlds that have a lot more data and detail in them, and higher res detail only where you need it, because you're being very selective as to where you want that high detail. It allows you to essentially have more for the same amount of hardware. And so you can start building for next gen basically right now. You should start re-architecting your engines for this kind of very granular and parallel workload, your PC engines. And you can start by integrating sampler feedback, right? First thing you want to do is make sure that you are selective about that data. And then you also want to build for DirectX 12 Ultimate. Here are two links that you can use. This describes sampler feedback, how you can use it. And that's a very important step to getting to a DirectStorage ready engine. I will also mention that there is going to be a limited DirectStorage developer preview, a closed preview in the summer of 2021. And if you'd like to participate, you can reach out to us at Ask Windy Storage. It's actually Ask Windows DirectStorage. Pretty easy to remember, Ask Windy Storage. With your name, email, and studio name. If you're interested in participating, we'll reach out to you if you're selected for that particular program. And you can, of course, get updates on our blog. One thing I also really, really want to mention is that we are very thankful for our collaborations with our industry partners. Without them, we wouldn't be able to essentially make a continued commitment to helping you get the most out of your hardware, something that we really are passionate about, and doing so in a very useful and standardized way through the DirectX family of APIs. And so huge thanks to them. Lastly, here's a little bit of helpful reading. You can get through this material to understand kind of where we're going, how you can update your engine, move it to get it into the future. And with that, I will thank you for listening to this talk, and am excited to see all of you build your engines for DirectStorage and next gen scenarios. So thank you, and have a great rest of your GSL conference.